So in this video, we will work to understand how we can use calculus and specifically integration to better understand motion in physics. Okay, so first off, we've already shown that we can use derivatives to better understand motion. That is, if we know the position as a function of time, we can always take a derivative of that and find the velocity as a function of time, and then we can always take a derivative of the velocity as a function of time to find the acceleration. Right? Or we can take two derivatives of our position as a function of time to find our acceleration. Right? So we can always go in this direction. Right? So what if we want to go the other direction? Right? If we know the acceleration as a function of time, can we figure out an object's velocity? And the answer is yes, but we have to use integral calculus to go in the other direction. Right? So if we know our acceleration as a function of time, we can integrate that acceleration as a function of time to figure out our velocity as a function of time. And it turns out we can integrate one more time, integrate our velocity as a function of time to figure out our position as a function of time. Right? So going in this direction, we can use derivatives. Going in this direction, we can use integrals. Okay. So let's work to understand this a little bit better. Let's just say this is our velocity as a function of time. This is our v versus t graph. We have a constant velocity of 5 meters per second. So given this graph, what can we say about a position as a function of time? Well, this is a relatively simple example. We know that distance is velocity times time. So if we're traveling at 5 meters per second, that means that every second we move another 5 meters. So we can, based on that, draw a position versus time graph. Now we don't know where we started, so that's going to be trouble, but we are going to be able to figure out the slope of our position versus time graph. But let's just, for example, let's just say we're starting at the origin, and we can draw a position versus time graph where we start off at the origin at x equals 0, and every 1 second we move another 5 meters, right? By 2 seconds I move 10 meters, by 3 seconds I move 15 meters, by 4 seconds I move 20 meters, right? So that's a relatively simple formula for this line, right? This line is given by 5 meters per second times time, right? It's a linear line with a slope of 5 meters per second, as we expect. And we can check that if we take the derivative of this formula, we get this formula, right? And we know we can go in that direction, right? So that was relatively simple. Let's check the calculus here. If we take our equation for relating position and velocity, if I plug into this equation my equation for velocity, which is in this case a constant, and I integrate that, I can get that time coming in, and then we get this constant of integration because again, we always get that with an indefinite integral, and as I kind of already hinted at, that constant of integration is going to be related to where your initial position is. Right? And we can actually check that. We can plug into our formula time equals 0. If I plug into our formula time equals 0, right? Time equals 0, this term goes to 0, so I get my position at time equals 0 is equal to c. Right? So we can always figure out your constant of integration if you know your initial position. So my position at time equals 0 is equal to that constant of integration, and we're typically going to use the symbol x of 0 to represent your position at time 0. Okay, so that gives us, and in this special case, of course, our initial position we said was 0, so that again simplifies our equation to this nice equation for this line. Okay, but it turns out, maybe there could have been a different initial position, and when we did the integral, we would have gotten the same answer, but we would have to solve for our constant of integration. And in this case, if our initial position was x equals 10 meters, then we plug in our initial position here. All right? And as we see, that just shifted up the entire line, but we still have the same slope. If we take the derivative of this equation, we still get the same answer here. All right? So the y-intercept here is our initial position, right? And that's going to just determine where we start, and then the slope of this line is going to be determined by your velocity. So given a velocity versus time graph, we can use calculus to figure out our position versus time. All right, and in either case here, we basically derive this formula, which is the definite integral, and we can show that for a definite integral, we can always figure out a displacement. That is, our final position is equal to the integral over velocity as a function of time from 0 to t, plus our initial value, our initial location. So if I move this over to the other side of this equation, the distance I've traveled, or my displacement, x minus x naught, is just given by the integral of my velocity with respect to time. Right? So in either of these cases, either I started at the origin and I moved this distance, this displacement, and this amount of time, or I started at x equals 10 and I moved the same distance in that same period of time. Right? So in either of these cases, this integral would be the same thing. Right? The displacement would be exactly the same. Right? It's only the initial position that would shift this graph up and down. Okay, so we've gone from an indefinite integral to a definite integral. Now let's talk a little bit more about interpreting our velocity versus time graph. If we take a look at that graph, we have in this case we have a constant velocity, and we know that distance traveled is just velocity times time. So the equation for that is displacement is equal to velocity times time elapsed. That's just solving our, for example, our average velocity equation for constant velocity for displacement. And we can note that the area of this, under this red line, the y component of this rectangle is just my velocity, right? And the x component is just delta t, how much time has elapsed. So I have the area of this rectangle is my velocity times delta t, right, base times height, which is exactly my equation for displacement. Right? So it turns out that if I know my velocity as a function of time, and I have a graph of that, I can just find the area under that curve, and that's equal to my displacement. Right? And that's exactly what this integral is telling us. Right? If we want to know the displacement of an object in some given period of time, I just have to integrate my velocity curve as a function of time. Right? So it turns out that this area under this rectangle corresponds to this distance. Right? So if I know my velocity as a function of time, I can figure out something about my position as a function of time, meaning I can figure out my displacement in that period of time. Okay? And if I have a harder situation where my velocity is changing with time, well, this is when calculus really comes into its own, right? I can always figure out the area under this curve, and that corresponds to my displacement. Even though my velocity was changing throughout my motion, I can still figure out how far I've traveled, right? So if your velocity is continuously changing, you're going to have to use an integral to handle that situation. But we can still think about it as being a lot of little rectangles, just like in the previous problem, right? So in this short time period, how far do I travel? Well, it's about the area of this rectangle, right? Because the area of this rectangle is my velocity times the time elapsed, right? And I can go to other rectangles, right, during this time period. How far have I traveled? Well, I'm traveling a little bit faster now, so the area of this is going to be a little bit bigger. I'm going to travel a little bit farther during that period of time, but the area is still given by velocity times displacement. I'm sorry, velocity times time elapsed, right? And during this time interval, I travel a lot farther. The area is much bigger, right, because my velocity is much bigger. Right, so by adding up all these rectangles, I can figure out my total displacement. And that's really what this calculus equation is telling us to do, right? It's just making these rectangles infinitely small, right? And so if you have a function of velocity as a function of time, you can always integrate that, find the area under the curve, and find your displacement. Okay, and this also works for acceleration, right? So if I know my acceleration as a function of time, I can always split this up into many little rectangles, find the area under this curve, and that corresponds to my change in my velocity, right? Acceleration is a change in velocity with time, so if I want to figure out my change in velocity during this time interval, I can just multiply my acceleration, which is this distance, times my time elapsed, which is this distance, and so the area of this box corresponds to how much my velocity is changed by. The area of this box corresponds to how much my velocity has changed by during this period, and the area of this box corresponds to how much my velocity has changed during this period. Right? My acceleration is increasing with time, so my velocity is changing more during this time interval than in this time interval. The area of this is bigger than here. Right? But again, we generally don't have to use all these rectangles. We can just use calculus, and if I have an equation for my acceleration as a function of time, I integrate my acceleration as a function of time from 0 to t. That tells me how much my velocity has changed during that time interval. If I integrate my velocity as a function of time from 0 to t, that tells me how far I've traveled during that time interval. Right? So if all you had was an accelerometer, which everybody does in their phone, if you know your acceleration as a function of time, you could always plot that as a function of time, as we've done here, find the area under that curve, and figure out how your velocity has changed as a function of time. And then you can always integrate that velocity as a function of time to figure out how far you've traveled as a function of time. So using just the accelerometer in your phone, you could basically make a Fitbit or something like that, right, where you can figure out exactly how far you've traveled on a run or on a bike ride or something like that. So something to think about. And again, something that people do every day in careers, in engineering and in physics and in all these different careers. So we'll do this in some example problems in future videos.